0 and you place the 1 there.
So that'll be 101.
101.
Okay, so with this, we can continue. So because of that, I'll just put the answers there for you. So that's it. So 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 0, and the last thing is what quadruple 1. Okay, so that's it for the first part of the question. Then the second part says that let 0, 1, and x be the independent digits in any arbitrary number system. So the first question, what is this number system's radix? Now, with this particular one, because we have been told that these are the digits 0, 1, and x, we assume that for us to be able to get a radix, it just counts the number of digits, which is going to be 1 for the 0, 2 for the 1, and then 3 for the x. So that leads us to what? A radix or a base of 3 for the number system above. Now in this number system, list the first 10 numbers. Okay, so similar to what we're doing by listing all the first 15 digits, in this number system that has 0, 1, and x, instead of the 0 and 1 like what we looked at, we need to be able to also know how we can list all the first 10 numbers. So the same logic rules here. We're going to have 0, 1, and x, which are already given from the question as the first 3 digits. So we are left to go with what? 7 digits. So that's going to give us 1, 0, which is this. 1, 1, 1x, x1, s. System. All we are looking at is I see some answer. Kayum, please go ahead.
Please, the first one, the first question, please, can you answer it like, mention the numbers like 0 to 15 or something like that, so that after that you convert it to the binary digits.
No. Why do you want to do that? That's a long procedure. We are already in binary, okay? So you don't have to write it in decimal and convert it back. You can actually look at it like this and then.
No, like in a rough side, like.
I know you can do that, but you don't have to do that. That's going to take much of your time. I get where I'm coming from. You want to write 1, 2, 3 all the way to 50.
After that, then you provide, like, you write this one as your answer.
Yes, you should write this one as you say for a given binary system, right?
Yeah.
It means that already in binary number system, we are not in decimal.
Uh,
Please, you understand? For a given binary number system, list the first 16 digits. Okay. All right. I saw another hand up. Minta Daniel.
Yes, sir. I wanted to ask, by listing the 16 digits, what if the 1, 1 comes maybe before the 1, 0? Will I be wrong?
If you write the 1, 1, which one?
The question 1, 16 digits for the binary number system.
Okay.
So if I bring the 1, 1 before the 1, 0, whilst I'm arranging it, maybe it didn't come in order as you have arranged, but it contains all the numbers that you have listed? Will I still be wrong?
It will be wrong. You don't have to mix them up. Okay. So you don't have to mix it up. If you mix it, like change the meaning. It's like you writing the number 10 in decimal number systems before then after you write the number 8. 10 comes in the 8. So in that sequential order, you need to do the right thing. Okay. Pascal.
Hello, sir.
Okay,
Yeah,
so
please say number 2. I don't understand number 2B.
Yeah, number 2.
Yeah, I don't. Yeah, if you can go over it.
good. So for the number 2, all we are saying is very simple. You have been given some number system, you don't know what the number system is. Because the X is a dummy value. But that number system is saying that it's independent digits in any arbitrary number system. The arbitrary can be 10, can be 2, can be 3, can be whatever system I think it is. The question on the table is, how do you first identify the base or the radix of this 0, 1, X number system? Now, if you check, you realize that in all the things we have been doing, even the decimal number system starting from 0, 1, 2, 3 to 9, they are actually like 10 digits. If you also come to the binary number system, there is 0 and 1. You count them, that will give you what? 2 digits. Now, in this number system, you can do the same for octals 0, 1, 2, 3 to 7. If you count the independent digits, you're going to get 8. The same applies to 16, right? 0, 1, 2, 3, all the way to 9. Then we have A, B, C, D, E. You understand? All these things are expected to be able to give you a fair idea of the radix of the base. So for this question, you are being told that 0, 1, and X can be independent digits in any arbitrary number system. So we assume that it can be binary number system or decimal number system. So all you need to do is just count the number of digits in this case, which is 0, 1, and X. That should give you a radix of 3. And that becomes the base of the radix. Then the second part in this number system lists the first 10 numbers. You have already been given the first 3 digits, 0, 1, and X. The next thing to continue is to be able to pick that and then continue from there. And that's what we're doing here. So if you come here, you cannot call yourself 0, 0. So hence we leave it like that. The 1, 2, we leave, the X we get there. So in that case, all we are doing is 0, 1, X. Then from there, since we cannot have 0, 0, because 0 in front of any digit is the same as that digit, we now move on to pick this one and concatenate it with a 0. That gives us a 1, 0. Then pick it 1 and then concatenate with this cell. That gives us 1, 1. Then pick the same one, concatenate with the X. That gives us 1X. Then when we are done, we can now move on to pick the X concatenated with 0. It can never be 0X because 0X is the same as what? X. So that's going to give us X0, which is here, X1, which is there, and then XX, which is here. Now we are done with the 2 digits. We need to now move on to the 3 digits. So for the 3 digits, same here, we cannot say triple zeros. Triple zeros is the same as 0. So now what do? We come here and then pick the 1 and then pick part of it, post part of it 0, 0, 0. So 1, 0, 0. You can have, if you are going to continue, that'll be 1, 0, 1, 1, 0, X, etc. I hope that answers your question.
Yes, sir. Yes, sir. Understood.
Okay. So I can move on small before I'm allowed for another set of questions. So octa has 8 digits 0, 1, 2, 3, 4, 5, 6, 7. And then the place values to be in what powers of 8. And if you're dealing with fraction, it will be a to the power negative 1 instead of a to the power negative 0. Because a to the power negative 0 is the same as what? A to the power 0, which is giving us 1. So we cannot start with a to the power negative 0, right? Because 8 to the power negative 0 will be the same as 1 over 8 to the power 0. And that should give us a 1. Okay. So when we write the 10 numbers that follow 7, octal, we cannot get 8, etc. So we have to now be able to move on from the 7. Now we cannot come to 1, 0, okay, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7. Then we cannot go ahead to also look at that of the 2, right? 2, 0, 2, 1, 2, 2, 2, 3, all the way to the next thing. Then we look at the 3 actually. Okay, so that's straightforward. Now we have a decimal number, we want to convert it into octal or radix of 8. So the question is that first we pick 175, we can convert it, and then we pick the 0.3125, and we can also convert that. Okay, so let's give it a try, everyone. We want to convert 175.3125 to radix of what? 8. Everyone, please try answer me.
Hello. Hello. Sir.
There is a trial question on the screen, so that's what we are solving now. Sorry.
Okay, so let's do it together, right? So converting the integer part, that we all can do, right? So we can easily be able to probably, in fact, there are a lot of ways you can go about it. Please stop writing on my screen, okay? Okay. Those of you are writing on the screen, please stop it. All right, thank you. So what can be done is very simple. We can actually go with the highest power of 8. We can do that part. Or we can also go with the what you know, right? The division by the base you are dealing with. So I'll use the division by the base aspect. You can also try the other one. That can also work. So I'm going to have 175. Albert claim. Stop writing on my screen. 175 divided by 8. Okay. Then what am I going to have? I'm going to be able to have 21 with a remainder of 7. And I pick the 21 divided by 8. That will also give me 2 with a remainder of 5. Then I can actually be able to have this. So in terms of you converting the 175, you're going to end up with the 257, right? So we start from the down to the top, okay, when you do it in that way. So don't forget, that's why sometimes it's a little bit dicey when you're going by it in that way. Then now have to pay the 0.3125, whereby you multiply it with respectively by 8, like we did for the other one, okay? So that you're going to have this 2.5. Then you can now go ahead to have 4.0. Then you can go ahead, now work is done, because even if you pick the 0 and multiply by 8, you're going to get the same 0.0. So that's one. You are now going to start from the top to the down. So that's going to give you 0.24. So when you put the two together, you're going to have 257.24, right? So that is it that you have to be able to know, okay? So remember, there are a lot of ways you can go about it. You need to be able to know which one you're familiar with, and then you're okay to go, okay? Now, to be able to explain more about the octa, all we need to know is that in terms of 8, we need to be able to be dealing with the digits in groups of 3. So when I pick any octa digits, it has to be represented by groups of 3. If I also go to hexadecimal, I have to also represent it by groups of 4. So the main concept is from here, right? If you can see, 8 can be given as what? 2 to the power 3. So when I have any binary digit I want to convert to octa, all I need to do is I have to group it in 3s. Now, in grouping it in 3s, depends on where I am, I can actually be able to know that a 0 in front of a number is always the same as a number. Now, if the 0 is after the number, if it's a whole number and the 0 is after it, it changes the meaning. So a typical example is if I have a number like, let's say 8, and I put 0 in front of 8, it becomes 08, and 08 is the same as the 8. Likewise, if I have the same number 8 and I put 0 after 8, it becomes 80. That 80 is a different meaning altogether. So we need to be careful, right? So what am I trying to say? What I'm trying to say is that if I want to be able to convert binary into octa, I can actually start by grouping the zeros from the right or the digits in 3s from the right to the left, okay? So let's look at this example. So for example, I want to be able to convert this binary to octa, right? All I need to do is that in the whole number part, I can now group it from right to left. Okay, so this one will be one of them. And then this guy will also be another one. But here there's no 0, so I can prepare with some 0 here. Okay, so if you check from the table, I can have 110. 110 from this table is a 6. Then 010 from this table is a 2. So it means that the whole part or the integer part gives me 26 or 26 in octal. Now, for you to be able to get a fraction part, so for fraction, the same example we use for the 8. In this case, I have, let's say, 0.8. Now, if I have 0.8 and I add 0 in front, I've not changed anything. Because 0 after that is the same as what? That same 0.8. But if the 0 comes before it, okay? So that becomes 0.08. that reads a different meaning altogether. This is not the same. 0.08 is not the same as 0.8. Okay, so what does it mean? It means that when it comes to the fraction part, I need to be able to do it from the opposite side, from the left to the right, to get in 3 digits. So this is 2 digits, 0, 1. So I can postpile the 0 here, and that will not change anything. So 0.010 is the same as 0.01 as we stand. And this guy is also the same as a 2. So at the end, my final answer after converting this 10110.01 to octal will be 26.2. That's it. Okay. Likewise, I can do the same. I can convert it back again to binary. If I pick the 2, I convert it into binary and then make sure that it's in 3 digits. The same applies to the 6 and the 2. That's it. Okay. So I can do that and I'm good to go, right? I see some hand up, but let me attend to some of them. Daniel, I've not heard it talk. Please go ahead. Daniel is not ready. Frank?
Hello, sir.
Yes.
Please, about the octal, the example. So when you look at the table, so the one that you do is 0, 0, 1, 1, 0, 1, 0. So can you also choose the number 1? Let's say the table. Can you choose the 1?
The table, can you choose the
one that you appointed to make it 001?
If I choose this 001, I am not seeing 001 here.
For the right side. For the right side.
The right,
Yes, please. So can you bring the 0? Can you do 001 for the or?
You mean 0.001? Is that what you are saying?
Yes, please. Yes,
That will
please.
change the number.
But I just explained that in here. See, that if I have, let's say, 0.8, okay, I can only add the 0 after the 8 to make it 0.80. I can't bring the 0 before it. If I bring the 0 before it, becomes 0.08. That will change the meaning. So in your case, you have 0.01. If you make it 0.001, the meaning now has changed. Please, do you understand? So
But
the
sir,
answer,
I'll get the same answer or different.
you get a different answer. The 0.01 gives you 2. What you are talking about is going to give you 1. They're not the same.
Okay, sir, I understand.
You get it now, right? Good.
Yes, yes.
And let me give it a chance to those who have not spoken before. Joshua.
Sir, please, can we use I learned one in senior high school. Can we use that one? The binary octal.
Oh, if that works for you, you can use it.
Okay. But it's similar.
Okay, so if that works for you, please, you can use it.
Thank you, sir.
Okay.
Thank you, sir.
You're welcome. Who else is on the table? Ebenezer Nyakon.
Hello, sir.
Yes.
Please, my question is on the binary. The example you gave, convert 175.31125 to radix of 8. So when I divided the 175 by 8, I had 21.875. In your case, I can see remainder 7. So I'm a little bit confused over
So
there.
This one, right?
Yes.
This. Okay.
Yes,
So
please.
when you divided 175 by 8, what did you get?
I had 21.875.
Good. Multiply 21 by 8. What would you get?
By 8.
You multiply 21 by 8.
I had 168.
168. Subtract 168 from 175.
That's 7.
Okay, so that's your 7 here.
Okay. Okay.
So
Okay,
some of
thank
it,
you. I get it.
I will let the T handle the tutorial part so that we can move fast. Okay, on that. So let me just move on for that. Okay. So we go here, hexadecimal quickly. So let's look at hexadecimal, right? So for hexadecimal, all we are looking at is very simple. Okay, we want to be able to understand how we can easily be able to get the various decimal equivalent. Hexadecimal will be A, 11 hexadecimal equivalent to be B, 12 hexadecimal with D, 14E, and lastly 15F. So that's the key thing when it comes to hexadecimal, right? Okay, so these are the digits, right? Here too, as digit is represented by group 4 bits as well, right? So the same way we look at the octal, so the same thing applies here. But these are the key things: 0, 1, 2, 3. When you get to 9, we cannot go to 10 because we are not in decimal. Rather, we are in hexadecimal. So from 10, we hit A, B, C, all the way to F. We've already looked at the applications from the beginning of the lecture, so I don't need to go back there again, right? So the decimal to the decimal equivalent is shown in the tables I've shown to you guys already, right? So we have 3B, 6E. We can easily get a place value using powers of 16. 16 to the power 0 for E, 16 to the power 1 for 6, 16 to the power 2 for B, 16 to the power 3 for 3. Then we can easily be able to now do that conversion. If you want to be able to convert this guy to decimal, all we do is that we multiply each of the decimal digits by their respective powers of 16. After all, you concatenate by adding them, okay? So this is by adding. So we add all of them, okay? Then we are good to go, right? So that's what you are doing. So whatever we get becomes your decimal equivalent. That would be 15,214 in base 10, okay? And now if you don't bring the base, we already know that we are dealing with base 10. That's the key thing, okay? So here too, we can easily be able to get the 0 in 4 bits, the 1 in that. 9 will be 1001. You already know that from beginning. A, which is a 10 in quotes, will also be 1010. B, which is an 11 in quotes, will be 1011. All the way to this C, which is what? 12. This D, which is like a 13. This E, which is like a 14, and then this F, which is like a 15, will give us quadruple 1. Remember, once we are dealing with base 60, we can never have any number which is 16. So that's why we have the F, which is equivalent to 15 in base 10. That's a key thing, okay? And all these digits have to be in groups of 4, right? So put binary numbers in groups of 4, that's neighbors, right? So half a byte is what 4 bits, and that 4 bits we call it what neighbor, right? So 1101, 1001, 0110, okay? So for example, then we can translate each neighbor representation into the hex form. That should be able to help us to be able to get it. So I can be able to know what is 0110. You can easily do your conversion, and that will give you the answer, okay? So this guy, I know that this will be 2 to the power 1, right? This guy will be 2 to the power 2. So this is 4, this is what? 2. So that's going to give me 6. So the whole of this guy should give me 6. Can you see that? They can do the same for the others. The work is done, okay? 16 is the same as 2 to the power 4. We already talked about this, so skip that, right? So if you have here, we can easily be able to now see how we can convert this binary to hexadecimal. Here too, same applies like we did for the octal. Okay, we prepared with zeros here, 4 digits. Okay, then we know that here too, in terms of going forward, I can have my first 4 digits, which is this. Then in here, I can prepare with zero, so 1, 2, and then 3. So this is 0, 0, 0, 1, which is the same as what? 1. So this guy gives me a 1. And then this 0, 1, 1, 0, right? From the table, you can actually do a conversion though, you know that. And that is actually going to give you a 6. And lastly, I can bring my point. And this is going to give me 0, 1, 0, 0. 0, 1, 0, 0 should give me a 4. So that's going to give me 16.4 in hexadecimal. Okay. Okay. We can do the same vice versa. Also, when I have 4, I can get a 4-bit binary equivalent, 6 4-bit binary equivalent, and then 1 4-bit binary equivalent. And that should end me up with. Okay. Octal to hexadecimal. The interesting thing is that when you want to convert from octal to hexadecimal to octal, always make sure that you convert to binary. Then you can now use the zeros in terms of the groupings. In this case, converting from octal to hexadecimal. Once I have the octal value converted into binary, I need to group it in 4s to give me the hexadecimal equivalent. That's it. So I have this 26.2. When I convert it into the binary and I want to be able to hit the hexadecimal equivalent, all I need to do is that this guy will have a 0 here, right? And I can easily be able to have the hexadecimal equivalent. 1, 2, 3, 4. I can get the hexadecimal equivalent. And this guy will be 1, this, so I can put zeros in front. And at the end, I can easily be able to get my hexadecimal equivalent also, right? So what do we have? So I assume the zeros I put them there. Then I can have my 4 for 0, 1, 0, 0. Then I can also have my 6 for 0, 1, 1, 0. Then lastly, I can have my 1 for 0, 0, 0, 1. That's it. So with the idea of converting binary to hexadecimal, you can easily be able to get it done by the groupings in 4 bits or in nibbles. Okay, because we know that 4 bits is the same as 1 nibble. Okay. Okay. So decimal to hexadecimal equivalent to, we can actually do that. I will not waste my time on this. So what do we do? Of 16 that will go into the 284. So the highest power of 16 going into 284 is 16 to the power 2. That should give us 256. Okay, so if you subtract this 256 from 284, that'll give you 28. So for the 28, you look for the highest power of 16 that will go into 28. That should give you 16 to the power 1. That guy is expected to give you 16. Subtract the 16 from this 28 you had. That should give you the 12. Now this 12, there's no way we can have 16, any power of 16 going to 12. So we leave this guy, and what do? What we are going to do is simple. We're going to be able to do it in that sequential order. 16 to the power 2 was there. So 16 to the power 1. Then at the end, our remainder became a 12. So instead of putting that 12 here, we are now going to put it in the form of what? A C. So that's going to give us 1, 1, C. Work is done. Okay. You can also go by the other approach, right? The repeated division approach, right? You look at 284 divided by 16, that should give you 17, okay? So if you do that, you're going to have 17 point something. So you multiply that 17 by the 16, whatever result you're going to get, to subtract it from the 284, that should give you your 12. The question someone asked me earlier on, right? Then what do? I can now come here and then pick the quotient, which is the 17, and then it will be divided by the 16. That will give me 1 with a remainder 1. And I pick the 1, 2 again, and I go with what? 1 divided by 16 will be a 0 with a remainder 1. That's it. So in this case, I don't have any issue to worry my head on. Why? Because This guy, which is a 16 and the 12, is going to have a C equivalent. And all these remainders are 1, 1. So remember, the previous ones you have been doing, you have been having it as 1 and 0. So in this case, because of the 12, we all need to be able to convert the 12 into the C. So that what do we have? We're going to have 1, 1, and then the C. Okay? Like we did from here. So this guy will be from the down to the top. Work is done. Right? Okay, so the 284 in base 10 will now give you 11C with a base of what? 16. So you can try your hands on this, okay? Because of time, I'll leave it as it stands so that when you go home, you try. But when you try it, you're going to have this 41E. So when you move to your various homes, right, give it a try, you're going to have either you're going to look at the highest power of 16 that will hit to go into 1054. We're going to do by the division, repeated division by 16, right? And then you're going to go by it in this way. But don't forget that when you are done, you write from the down to the top, okay? As decimal to decimal, right? So I'm going to have 2 dB in the hex form, and I want to be able to convert it to the decimal or a base of 10 or a radix of 10. So what do? All I'm going to do is I'm going to look for the place value, right? So that's it. So what am I having? I'm going to have 2 dB, which basically is expected to give me this guy. We know for sure, if I'm starting from the B will be what? 16 to the power 0. So I'm going to have 16 to the power 0 times the B. And B, we already know in decimal is 11. Then when I come to the D is going to be what? 16 to the power 1. So this guy is here. This guy is also here. So that's going to give me D times 16 to the power 1. And my D is the same as a 13. This guy is the same as 11. And then this is the same as the place value will be 16 to the power 2. So I'm going to have 16 to the power 2 times 2. So when I do all those things, what am I going to have? I'm actually going to have the final answer in decimal, which is actually going to give me 512 plus 208 plus 11. That'll give me 731. Okay. 10. Now, a comparative can have the binary equivalent as quadruple zeros, octa. Basically, this octa is expected to have 3 zeros to be on the safer side. Even look at it in that way. But the key thing I'm looking at is that you need to be able to understand the fact that if you have anything you want to be able to convert, you need to have it in groups of 4 if it's hexadecimal, in groups of 3 if it is octal, and then that's the main thing. So basically, this one rather would have been the hexadecimal equivalent of the binary. Okay, so if I pick this hexadecimal equivalent, in terms of it converting to binary, I'm going to have it in this. Okay. So we look at an application example. I've uploaded a particular ASCII table on your Sakai page. And ASCII basically is an American Standard Code for Information Interchange. And this basically is expected to have every key on your keyboard, right? It's going to assign the standard binary code to letters, numbers, punctuation marks, wild characters, anything you can think of, right? Operators and anything that you can have as far as it is being used to the computer system, right? It's a 7-bit, ASCII is a 7-bit character set that contains 128 characters. Basically, the 8 bits is often used for error detection or parity bits, right? So we can have a typical example here. Digital, the word is called digital. So we have a capital D, and then the rest are lowercase. So the capital D in terms of the ASCII will be what? 1000100. Okay, so if you check, this is the binary code for the character D. That's a key thing. And then we can also get the I. So if you check what I've uploaded on your Sakai page, you should be able to have that. Just a second. Mr. Omar. All right, so that's basically it. So we can get the hexadecimal code. You can forget about this for now. We stick to the character to the binary code, and then that's it. So check Sakai. There is a particular ASCII table I've uploaded there for you, right? Let's look at the binary coded decimal, right? Remember here too, I've given you the application in the beginning of the lecture slide. So look at that as well. Now, the main key thing I want you to know is that the BCD will replace each decimal they get with a 4-bit binary code. It looks like there's a decimal, but there's a difference because in this case, I'm picking only the decimal number they get 0 or then and then I am picking each of these decimal digits and then finding a 4-bit or a nibble binary equivalent of each of them. That is it for the binary coded decimal. In the application, please go and refer to the beginning of the slides, right? Convert 6469, which is in decimal, to a binary coded decimal, BCD. So what I'm going to do is that I'm going to pick the 9, I'm going to pick the 6, I'm going to get a 4, and I'm going to get a 4-bit binary equivalent of each of these digits. That's it. Work is done, right? If I'm able to do that, that's it. I'm okay. So that is about the BCD. So for your exercise, right, you're going to find a decimal equivalent of this guy, right? So we want to be able to look at the binary equivalent of it. Remember, our key stroke is to be able to get the equivalent from 0 all the way to 9. If the number give us like a 10 or 11, then it's not an equivalent, it's not a valid BCD. That's another thing I want you to know. All right. So if you check this guy is 1011. If I check 1011, this is going to give me 2 to the power 0. That'll give me a 1. This is going to give me 2 to the power 1. That'll give me a 2. 2 to the power 2, 2 to the power. This guy is going to give 2 to the power 3. That should give me an 8. So this is going to be 8 plus 2 plus 1. That should give me an 11. And if you check, 11 is not a valid BCD. Why? Because we want the end results to be outputted to either 0, 1, 2, 3, all the way to 9. That's it. Work is done. Okay. So this will let us know that it is not a valid BCD. So not possible because 1011 giving us the 11 is not a valid BCD, right? So your assignment, you can convert this guy to this. Here too, because of things I want you to get home done, you can actually do it when you get home. So when you do it, you should be able to hit with this value, right? You can go and confirm that when you get home. Okay, the answers are already there for you. In summary, you have been able to look at digital electronics using a binary or base 2. So the plus 5 volts normally represented with a 1, okay? And then the 0 volt represented with a 0. So this guy, when he's going to go into the computer system, you realize it's going to be like this. These are the signals. Okay? Whereby this will be your 1, which is your plus 5 volts. This guy will be your 0, which is your 0 volts. This guy too also be your 0. This guy will be your 1. This is going to be your 0. It's going to be your 1, your 1, your 1, probably your 0, etc. Right? So that's it. So when it gets into the CPU for it to be computed based on the ALU, arithmetic logic unit, we're going to look at it next week. it shouldn't see it as ones and zeros, but rather it's going in as this particular digital signal. So if there's another one it has to be concatenated with, that also comes with its own digital signal before they can actually use it. But we use the zeros and ones for teaching purpose, for understanding purposes. But when you get into the brain of the computer, you don't see the zeros and ones. You actually see the digital signals. That's another thing I want to establish with you. So that's why we have the +5 volts denoting a 1, the 0 volt denoting a 0. Analog electronics operate on continuously varying electrical stroke physical magnitudes like the temperature, the pressure, the weight, the velocity, and etc. Right? And then another thing you have to also bear in mind is that we have to be able to know that these digital signals are also the same as discrete signals. Okay, so discrete signal is also another key thing. And then at the end, we also saw the number conversion from binary, octa, hexadecimal, BCD, or vice versa, right? So that's what we looked at. Then the recommended test because that. That's it. Any question? Joshua. Yeah.
Probably the octa table, is it composite for you to for us to memorize, or you have a lot of doing?
The octa to which one?
The table, the octa and the hexadecimal table.
No. You don't have to memorize it, please. If you check, I was actually even doing it, even when I got here. You can actually do it on your own. You don't have to memorize. See this thing I was doing, right? So you can actually be doing your conversions yourself.
Oh, okay.
You don't need to memorize it.
Okay.
I saw another hand up. Joshua.
Yes, sir. So please, when you compare the decimal to the hex, you ended at 15. Is it possible maybe we would be asked that we should change 16 decimal to hex? Is that possible?
16 decimal to hex. That's decimal, decimal number 16. You want to convert it to hex. Oh, you can
Yes,
easily
sir.
convert. What do you think? If 15 gives you what? Is it F, right? What does 15 give you? Let's go back to the table.
G.
F. So if you are having F for 15, and then now you have 16, then what is 16 going to give you? 16 basically is going to give you 1, 0.
Okay.
Are you with me? So that's something I want you
Okay.
to note of.
Okay. Meaning the letters of the alphabet ends at 15.
Conventionally, right? Yes, please hold on for me. I'll be there shortly. Right. Yes, when I come over. Right. You're welcome. Guys, let's continue. So your question is answered, right?
Yes, sir. So I was asking whether the letters of the alphabet ends at the F.
Yes, it ends with the F.
Okay.
So anything after the F, you just have to do the concatenation, right?
Oh,
so
okay.
is 9, 0, your 17 will be what? 1, 1, and so forth.
1, 1. Yes. Okay.
Okay, is there any other questions? Sorry, the master students are writing exams. I have to move to that place. That's what I'm trying to. Joel, Sophia, let me hear from you guys. Joel, Sophia, any of you? Pascal, Prince?
Okay, sir. Please, I wanted to ask, in an IAL exams, if you are asked to use the ASCII to spell a word, will the ASCII be provided, or we have to know it off head?
Oh, it will be provided.
Oh, okay.
To be provided. That's why I've given you that table on Sakai. Okay, to be provided. That's a very good question. All right, thank you. Joel, Pascal, Prince, any of you? Calvin, Samuel?
It means that we'll be using only this base, and like the computer uses only the 3 bases you mentioned, radix. So
the computer actually uses the base too.
So it doesn't use other radix like radix.
The other ones they all have to be converted to the base 2 for use.
Okay.
Okay. All right. Prince.
Okay, sir, please, Calvin, this is Calvin.
Okay, please go ahead.
Okay, please, with the Zoom, I think it's a bit unstable. So I don't know if you try and get your team Microsoft Team link work fixed, because the least chance it. So kindly try and work on your Microsoft link. We beg you.
Is it the same issue with everyone?
I said the Zoom link is not that stable. The slightest thing on and it goes off.
Is it the same with everyone? It's not stable with everyone, or is the one having the same issue?
My other colleagues were all complaining. Some of them were also complaining earlier.
Please let me hear from you. Is it the
Oh,
same
it's
issue?
fine. It's been fine.
To me, I think
I
it's
I think
maybe
the
the
Zoom is
person's data
better. The Zoom is
connectivity.
better.
Yeah, mine too.
Yeah, for us, the Zoom is way better than
Oh,
the other one.
yeah. The Zoom is okay.
So me maybe the person's internet connectivity is maybe is
It's
poor.
not about my internet. I'm having like
Please, you guys should
it's going on.
Okay, it's fine. So I'll speak to Michael Kologu on that. And then if anything, I don't have to provide a team thing. We are supposed to put it on Sakai for you. So we have to discuss on making. Okay. So that automatically we use the same link. If not, I'll have to use the Zoom for you guys. But I'll talk to him. Charles, you can do the same to Michael for me. Okay.
Okay, sir.
All right. There's nothing I have to rush. Anything else?
Sir, please,
sir,
mine
please, I
is
want
not
to
actually
ask.
a question.
I'm a chief
Just
invigilator
wanted,
to exams there about writing, so I need to move them.
sir, please, a quick one. I just wanted to plead with you that maybe on the next lecture, if you could probably slow down a little bit in
Oh,
the presentation. Yes, sometimes you are quite too fast. Yes, please.
I agree with my colleague here. So
Thank you.
please, slow down a little bit for us.
I will do that. I will do that. Thanks for doing that. Please, anything else?
Please, would you upload the recording on Sakai?
I was the one who recorded. I think some of the police recorded, so they can probably share the link with me. So please, those
Oh,
who are
okay.
granted the permission to record, maybe you can upload it somewhere, and then you can share the link on your feed. So that's okay. Okay. You will get a team program. The team will help so that when it's done, it will actually request for you to for the company. So first, probably draw Matriculable attention, right?
Okay, Doc, please, I'll do that.
Don't work on the Zoom, the teams and share on this.
Okay, please.
Okay, all right. I think there's nothing.
But you really need a recording.
Time is up. Once again, you have a
You really
WhatsApp.
need a recording.
So please make sure you get the link on the WhatsApp page, and then we are good to go. Right? I'll see you guys over the next week at the same time. 1 p.m. Right? I've uploaded material for you on Sakai. So all the best.